Okay, hyperconjugation. It is the least effective way to stabilize a carbocation. We've talked about that because we're not actually moving any electrons. So what's so great about this? Someone had a really great analogy of this, that this essentially is like a limb got cut off, but we're putting a Band-Aid on it and hoping it grows back. Yeah, more or less. So it's better than nothing, though, right? So it will be better if we can actually move electrons, right? Pi bond resonance would be better. Lone pair resonance would be the best because we get a full octet. Hyperconjugation is better than nothing, though, right? It's better than nothing. Let's make this an H, just to show an example here. So this carbon right here is this carbon, just so we can all get on the same page. This carbon is this carbon. So even though it's not perfect, it's better than nothing. Now, essentially, way to think about this, so we have this empty p orbital and 2 bonds away, right? We talked about this. This is all about, right, sigma bonds, 2 bonds away. And I'm going to add another caveat, sp3 hybridized sigma bonds, 2 bonds away. All right? Imagine, right, of course, in every bond is what? In every bond, there are electrons, right? There are electrons. And even though it's not perfect, there's electron density in this bond. And it's kind of like you have this like empty p orbital, right? That's like straight. And then if you imagine my elbows are together, right? So here'd be a pi bond, right? Everybody have pi bonds? They're lined up perfectly. Now, if you just like crooked out one of your elbows, right? It's not perfect anymore, but it's still better than nothing, right? It's like this electron density is just kind of like sending like a little bit of static that way that helps stabilize it. So this carbocation, of course, is sp2 hybridized, has that empty p orbital. And it's good to be able to look at a molecular orbital picture, but then also look at it as right here, right? As well. So sigma bonds, 2 bonds away. It doesn't have to be carbon or hydrogen bonds, any sigma bonds. So these could be, there could be multiple carbons here. There could be an oxygen here. It doesn't matter what it is. Sigma bonds, 2 bonds away, as long as they're sp3 hybridized atoms. Okay? That helps? Why does this matter? Excellent question. What? Okay, who cares, man? Like, what's going on here? So let's just take a look at this exact example. This is what kind of carbocation? Primary, secondary, tertiary, allylic, or benzylic? It's a secondary carbocation, right? Can we make it more stable? Is there such thing as a more stable carbocation? Yes. And we'll do a rearrangement if that's possible to make a more stable one. Always more stable, right? Hyperconjugation kind of tells us where these rearrangements are going to take place. Because now look, here's my empty p orbital. Here's see those electrons I have in that CH3 group? What if, right, all of a sudden this happened? Boing. And now this went here and this became a carbocation. Right? Empty p orbital. Sigma bond, 2 bonds away, kind of crooked, right? Not lined up perfectly. But if we do a full rearrangement, what was the hyperconjugation becomes a carbocation. So take a look. Let's see if I can draw it here. There it goes. All right, this is that CH3. Hyperconjugation buddies are the things that become rearrangement partners. Right? So what happened here was this went there. Now, why would it do that? It only would do that if you make a more stable carbocation. So by looking at the hyperconjugation buddies, you can look at things that are able to rearrange. Everything that rearranges has to be 2 sigma bonds away, 2 bonds away, right? So it does matter which one goes, right? So let's just pretend, I'll add this in, a little layer. What if this was an H? And this actually won't work now. I'm not going to do that. I can't do that. Because only rearrangements happen when you make a more stable carbocation. So if we look at this one, right? What kind of carbocation? We start with a secondary one. What do we just make? Number our atoms. We should have done that originally. 1, 2, 3, 4, 5. So let's say carbon 2 moved, right? So now there's carbon 2 here. Other way around. Carbon 2 moved, now it's right here, right? So there's 2. It's now bonded to 4. There's 1. I put 4 twice. That's a 5. 5, 4. 3 lost it. So 3 has the plus charge now. That's what rearranged. Now, why pick a methyl? Obviously, there's only methyls there. But I had to form a more stable carbocation. So once you do a rearrangement, you must form a more stable carbocation. So how do you know which group rearranges? It's only based on what the final product is. Right? So don't move a hydrogen if it's going to go from secondary carbocation to another secondary carbocation. Move a hydrogen if it goes from secondary to a tertiary, right? But you always got to make a more stable carbocation. So this is all good. Hyperconjugation, carbocations. Carbocations are electron deficient. So if I'm an empty p orbital, I like hyperconjugation is good for me because I'm an empty orbital. Hyperconjugation, right, shows these electrons, donating some electron density or even fully rearranging, right? So this, again, this was a full rearrangement. The red is rearrange, but only to more stable. But what if there's been a carbanion? Is hyperconjugation good or bad for carbanions? What's the charge on a carbanion? Positive or negative? Negative. And hyperconjugation donates electron density. Do you think carbanions want hyperconjugation? Heck no. Right? So it's just the opposite rule. Carbocations like things more substituted. Carbanions like things less substituted. Right? Less substituted. A less substituted carbanion is actually more stable than a more substituted. Just the opposite of carbocations. For the exact same reasoning, though. Opposites attract.